mirror symmetry for Claviel threefolds roughly says the following. If you have some Claviel threefold where X is a complex three-dimensional manifold, this is a symplectic form compatible with the complex structure, so it's actually the Kähler form. Omega is a holomorphic, nowhere vanishing holomorphic three form. Yeah, so it defines an isomorphism from this holomorphic line bundle to the trivial holomorphic bundle. And the mirror symmetry says there should be another Claviel threefold called the mirror Claviel threefold. And the mirror symmetry should relate the A model on X, which is defined in terms of the symplectic structure of X. So mirror symmetry is A model on X defined by symplectic geometry of X should be equivalent to B model on this mirror X check defined in terms of the complex structure on the mirror. So there are many mathematical aspects of this. So one consequence of such an equivalence is A model topological string theory on X should be equivalent to the B model topological string theory on the mirror. So, but what does this mean mathematically? So these are, mathematically, these are Gromov-Witten theory of X omega. So Gromov-Witten theory is a theory of enumeration of curves, and actually it can be defined for compact Kähler manifolds, not necessarily Claviel, not necessarily three-dimension. And it can be viewed as the mathematical theory of A model topological string, and the foundation was established in the late 90s. So, so for the Claviel threefold case, this gives us in particular some generating function fg. So this is a generating function of genus G, Gromov-Witten invariants of X. These are it is defined by counting genus G curves, holomorphic curves in X. So on the B model, so when the genus zero theory is just the variation of Hodge structure described in terms of the period integral of this holomorphic three form along 3 cycles. So for higher genus, so this is the BCOV theory of Bershevsky, Chekhov, Oguri, and Kumran-Vafa here. So this gives you some B model generating function. So, and under mirror symmetry, so this should be related to this. And here, so the mathematical theory of higher genus B model is still being developed. So there's Costello, Lee, and so C. Lee will probably tell you more on Sunday. So for example, the most famous example is when AX is the, say, quintic threefold defined by a degree 5 polynomial in the projective space. this is a compact clubial threefold whose, so then in this case, Fg is a formal power series in one variable Q. So whose coefficient, so this is the genus G degree D Gromov-Witten invariance of the quintic threefold. And using this, there are mirror predictions. So yeah, so I think it's like 91 Condelas, De La Osa, Green, and Parkers. So mirror conjecture for S0, and in 1993, so conjecture mirror form of F1, F2, yeah, and probably more. And there are a lot of development, and in 2006, Wang, Clem, and Quackenbush, so they can have mirror conjecture of Fg up to 51. So this conjecture on F0 was, oh, is it visible? Okay, so this conjecture was proved by Giventhal and Lianliu Yao in 1996 to 7. And about 10 years later, so the conjecture for BCOV conjecture on genus 1 mirror formula was proved by Alexei Zinger but this relies on early work on reduced genus 1 Gromov-Witten theory developed by Zinger and Lee Zinger. And also, I should say that yeah, maybe let me just write it here. So in 2006, there's Malik Panda has an algorithm, mathematical algorithm, based on degeneration, computing this NGD for any genus n degree. So there's for any genus fixed, for any such a number, in principle, one can compute it in finite time. But this finite time might be very, very long. And to my knowledge, so now it's 2017, which is 10 years after this. But this F2 is still conjecture. Okay, in Junli's talk on Sunday, he will tell you another algorithm of computing this NGD. So in general, higher genus Gromov-Witten invariance of compact clubial threefold, such as a quintic threefold, and higher genus mirror symmetry are very important, but also very difficult problem. So today I'm going to tell you yeah, so a case, so mirror symmetry, some case where we can say much more. So this is, so this O genus mirror symmetry for toric Calabi-Yau threefolds. So it's a Calabi-Yau threefold which contains the complex algebraic torus as dense open subset, and the action of this torus extends to X. And so for later convenience, the Calabi-Yau condition tells us there's a subtorus. So this is a subtorus X trivially on this line bundle, trivial line bundle. And then this is so we also consider so we call this Calabi-Yau torus, and there's also this maxima compact subgroup. We call it Calabi-Yau compact torus. Okay, so just some notation. So these toric Calabi-Yau threefolds are never compact, but advantages with this torus action, we can use the torus action to compute their Gromov-Witten invariance. So they are much more computable, and we can actually prove homogeneous mirror symmetry in the following sense. So now, on A model, so this is symplectic toric Calabi-Yau 3 manifold, and we can be a little bit more general or orbifold. So it can be, as a complex manifold, it's some GIT quotient of CK plus 3 by the action of complex torus. So this means you take out some closed subset. And on the B models, so Hori and Vafa has so this toric Calabi-Yau threefold can be described in terms of combinatoric data, and there's a standard way to write down this mirror, Hori-Vafa mirror. So it is of the following form. First, it comes in families. Yeah, so if you restrict this action to the compact k-dimensional torus, you get some moment map to RK, and S can be also written as a symplectic reduction. And in this description, by choosing different R, we get different symplectic structure, and K will be the second Betti number of the quotient. So this is the number of Kähler parameters. So on the other hand, this mirror is another non-compact Calabi-Yau threefold, which is of so here, it's actually a hypersurface in C2 times C star 2, and it's given by this, where this is some Laurent polynomial in xy determined explicitly in terms of the data of x, and the coefficient depend on q. So if right now you have k parameters, and on this side, this is a family of dimension k. So q actually involves k complex variables. So here we can actually have, similarly we can have so these are Gromov-Witten invariants. These are the Gromov-Witten invariants. So because these X are non-compact, so they are actually defined and computed by using this torus action. So moreover, we can also define open Gromov-Witten invariants, which count holomorphic curves to X with boundary in some Lagrangian introduced by Agnagic and Vafa. And these Lagrangians are invariant under the action of this compact Calabi-Yau 2 torus. So these can also be defined and computed using the torus action. So how about, so we can so here I don't understand much this BCOV theory, but fortunately in this case, so it was suggested that this can actually be reduced to a theory of Orrington invariance omega Gn. So these are actually on the mirror curve CQ phi. So where CQ is the affine curve in C star 2 defined by this equation. And this is a one form. So this is this might look problematic because of this log is multi-value, but one can make sense of this and define this. So this So the Bouchat, Clem, Marino, Pascati. So they made this remodeling conjecture in the paper remodeling the B model. So which says this BCOV theory can be reduced to this series just on this affine curve in C star 2. And we will see later these are simple objects. And then the conjecture is actually basically, so under the mirror symmetry and combined with all this, so omega 0 gives you the, under mirror symmetry, so omega G0 will correspond to genus G closed Gromov-Witten invariance of your toric-Calabi-Yau threefold and FGN. So this is when n is greater than 0. So this is proved by, well, Aina and Orenton for toric-Calabi-Yau 3 manifold. And my collaborator and myself, so we generalize to the orbifold case. And also our proof in the orbifold case also also gives a new proof in this case. Okay, so this is just an outline of our results. So let me give you, so if we want to, if I give you the precise statements of the most general setting, it will involve a lot of combinatorics. So instead of doing that, let me just like give you more details on, so one example. So for example, you take x be C3 minus 0 cross C modeled by the C star action, free C star action with weight 1, 1, 1, minus 1. This is the total space of O minus 3 over P2. And I can draw a picture, one skeleton, which is a union of zero-dimensional and one-dimensional orbit of the torus action. So it looks like this. So you have 3 torus fixed points in the zero section P2. These are the 3 one-dimensional orbit closure, which are P1. And over these 3 fixed points, you take the fiber of O minus 3 over P2. So there are 3 torus invariant lines. So you have this. So this compact action by compact Calabi-Yau torus give you a moment map to R2. So if under this one scalene gives you a planar trivalent graph. And then in this example, So in this example, CQ can be, I'll just tell you, CQ can be, the mirror curve for this particular example can be written down very explicitly. Yeah, and its shape is just like the fattening of this. So it's a torus with 3 punctures. And also there's a natural compactification. So although this is a simple example, you can see what happens in the general case. What happens in the general case is that for any toric Claviel 3-fold, so you have this one skeleton, which is a union of 0-dimensional and 1-dimensional orbits. And then under this moment mapped to R2 by the compact torus, you get a trivalent graph in R2. So vertex correspond to the fixed point, compact edges correspond to the invariant P1, and non-compact edges correspond to the invariant complex line. And then your mirror curve, the shape of mirror curve will always be like the fattening of this. Yeah, so it's like this. Oh, and where are Lagrangians? So yeah, actually, so for example, so this so-called agnetic Vafa Lagrangians, yeah, so it looks like, so it will intersect, say, invariant line along a circle, and under this is mapped to a point. And this, so this is just a rank 2 bundle over a circle topologically. Now in this particular example, so we have this beta. So this represents the second homology class of X. Yeah, with integral coefficient. Yeah, and this is a relative, and this disk bounded by this Lagrangian called alpha. So in this particular example, this is generated by where this beta is a generator of second homology with integral coefficient. So for more general case, you will have this alpha, but you will have, so this will be higher rank, actually rank K, and you will need K generators. But in this particular case, so you define, so here X is this particular case. So this is, yeah, I'll just write down some integral. Okay, so this is just parameterized holomorphic map from a genus G curve to X, which is O total space of P to O minus 3 over P2, and then such that so this tells us the G, and such that it is the push forward of the fundamental class is D times beta. So yeah, any curve, any holomorphic curve has class a multiple, integral multiple of this beta. And this means, so this means we consider this moduli, and we consider the torus invariant part. And one can actually check that if you have a map in this moduli space, which also fixed by this torus action, then actually it will factor through the one skeleton. So the image will just lie in the one skeleton. So, and then there are some way to define this kind of equivalent invariance. So a priori, so when you define this equivalently, so instead of you will actually get some rational function of U1, U2. So where U1, U2 are the equivalent parameters. So because there are two of them, because it's a two-dimensional torus. And so, but it turns out that this is some theorem that this is actually doesn't depend on. It's actually a rational number independent of this equivalent parameters, and one use this. In this case, again, the genus G Gromov-Witten invariance of this toric-Calabi-Yau threefold is a generate formal power series in one variable D. So in the general case, you will just have like more Qs. And for this open invariant, so this is so it's also defined by some equivalent integral, and in this case, it does depend. It's actually a rational, it's actually a rational function in U2 over U1. So let me just say geometrically, what does this parameterize? So this parameterizes holomorphic maps from a Riemann surface of genus G with our boundary components, with M boundary components. So there are N holes and G handles. So map to the target X with boundary in this L. So this tells us the G and N, and actually, so the push forward of the fundamental class is now a relative class. It's D times this beta plus this times alpha. And if you look at Ri, so the boundary of this alpha is this circle. This actually generates the first homology of L. Yeah, so again, so you take this moduli space and take the torus fixed part, and you can check that if it's in the torus fixed part, then the image must lie in this one skeleton. And then we can define and compute it in this way. So this is in general, yeah. So in order to get a number instead of this function, so what we do is introduce like f, which is an integer called the framing. Then we make this specialization. So this is equivalent to specialize it to a one-dimensional subtorus with slope f. So yeah, so these invariants are defined and computed in this way. So then so actually this kind of fixed locus, so what happens is your curve can have nodal degeneration, and higher genus component will map to constantly to this fixed point. So for convenience, I take, so I define this to be FG0. So we can prove the following theorem. So this so here I have n g d mu1 to mu n x L f. I form a generating function. Now I have one n additional variable to keep track of this winding numbers mu I. So this is the generating function of all genus open invariant. So this is the definition. And the theorem is this has some graph sum formula. Yeah, so the proof, so the idea of this proof is, so let me just say the idea is proof. So we use localization, and then we can express it in terms of closed descendant Gromov-Witten invariants, which are more general than the closed invariants here. And for those, so the proof is localization plus a Giventhal's formula for generating function of descendant closed Gromov-Witten invariants. This is in the manifold case, and in orbifold case, we use zones generalization. So we get such a graph sum formula. So this is theorem A for A model. So for B model, we have this, recall that we have this mirror curve. So this is for that particular toric-Labial threefold, but in general, it's more complicated, but can be written explicitly. So here there's a choice of f. So here this corresponds to a choice of x tilde, which is xyf. So this gives you a map to C star. So we choose generic f such that this is holomorphic Morse, meaning that this is a ramified cover such that all the branch points are simple. So then, so this omega gn is defined, so omega 0, 1, so the initial value so these are like unstable case. These are like disk invariant. This is 0. And omega 0, 2 is. So this is a symmetric meromorphic form which has a double pole along the diagonal satisfying certain condition. But we know how to normalize it such that it is uniquely determined by the original toric-Labial threefold. So these are the initial values. And this corresponds to like the annulus counting holomorphic. This should correspond to counting holomorphic disk and counting holomorphic annulus. So in the stable case, which is so in this stable case, so this is meromorphic symmetric M form on the compactified mirror curve, nth power of compactified mirror curve, as holomorphic on if you take away the critical point or ramification point of this x. So, and it's defined recursively by the Einar-Orenton topological recursion. So this is, so I don't have time to, so this is a very long expression of topological recursion. But the thing is that the unique solution of the topological recursion has a graph sum formula. So and then we take this so then we have a theorem B so recall we have this mirror curve. this is x. So this omega gn is actually holomorphic near this point. So near this puncture, x tilde is a good local coordinate. So we can define like the B model potential So these are local good coordinates. So you can pull back it to the nth power of this small disk. So this is power series of q and x1 to xn in terms of q and x1 to xn. So we actually prove that so this is So we use this graph sum formula, and we need to take this graph sum formula, expand it near this point, and we get this graph sum formula of the genus G Gromov. So get the B model potential, and there's a graph sum formula, and actually it's sum over exactly the same set of label graphs. So now to prove this all genus mirror symmetry predicted by BKMP, so it remains to show that for each gamma, WA is equal to WB. So, so this is done by the following. So this, so WA, so yes, so the weight of the vertex actually, weight of vertex and the weight on the edges in both hand sides depend only on the genus G closed Gromov-Witten invariant. So to match so we use Coase-Cody Iritani-Zheng genus 0 mirror theorem, and plus Bohan Fang and myself, and also Xianhua Zheng has genus 0 open mirror theorem. So this helps us to match the vertices and edges. So depend on our functions on closed variables. And this helps us to match the contribution from the open leaves. So for n, there will be n open leaves. And so the n open leaves will depend on both the closed and open variables. So this is how we prove this. OK, thank you.
Any questions? Yeah, Conan.
How close is there a mathematical definition of the refined Gromov-Witten invariance? Are people thinking about
refined Gromov-Witten invariance? I don't know. I only know people have refined Donaldson-Thomas invariance. I myself don't know how to define refined Gromov-Witten invariance.
So in this context, do you know how to get the formulas involving the extra parameter, the Napier partition function?
Nekrasov partition function. You mean that with 2 parameters? Then I don't know, because if you have general two parameters, it should correspond to refined invariance, right? But these are not a refined invariance.
That's my question. How close are people to defining the refined one and proving it? So this naturally should be extended to the refined case.
Yeah, I myself don't know how to extend the refined case. Yeah, so maybe I should say, sorry, so but we generalize it to the orbifold case, and our result in the orbifold case is actually more general than their original conjecture, because we allow our agnetic Rafa brane in the orbifold case to have some stacky structure along a circle. And in that case, one brane will correspond to several punctures on the mirror curve, and you need to span it over several punctures and make combination to match the A model open orbifold Gromov-Witten invariance. Yeah, sorry, I cannot answer your question.
Okay, let's close here and come back at 10 minutes.